Hello students, welcome again to the new segment. In this segment, we will be looking at the intuition behind the nearest neighbor classification algorithm. So let's start. So the very first thing we should note about the nearest neighbor algorithm is that whenever it's going to classify a new unseen instance, so it's going to compare it with all the available data points that are present there within our data set. So in that case, it's a little bit computationally expensive, but that's how it works, that for each and every unseen instance that it wants to classify, it's going to compare it with all the available data points that are present here within our data sets. Right? So let's see a little bit more deeper into the working of this classifier. So before that, let's cover the essential philosophy. So let us suppose that we have information regarding different kind of birds, and that we have already stored within our database, and we call them as training records. So then a new bird has been encountered, and we want to classify based on these available records of birds that what kind of bird it is. In this case, it happens to be a duck. So we are going to look at very similar instances, like suppose that if it walks like a duck and quacks like a duck, then it's probably a duck, right? So we are going to compare the properties of this duck with these available records of the different kind of birds, and then try to choose the nearest k records corresponding to different kind of birds, and then probably these will take part as our predictions, and they will become our predictions for the future. So that was the essential philosophy. Now, in order to build classifier based on the nearest neighbor approach, we need at least three kind of information. The first thing is the set of stored records, right? So we need to have all the records, all the available database points, or all the available instances information in order to classify a new instance. The second requirement is a distance metric, a particular distance metric, which will show us how similar or how dissimilar a particular data point is from the other data point. And then finally, we need to determine a value of k, which will be the number of nearest neighbors that will take part in the classification algorithm. So in order to classify an unknown record, first thing we need to compute is the distances of all the points from the unknown data point that we have, and then we need to identify the k nearest neighbors. So based on these distances, we need to sort them out in ascending order, right? And then we need to determine the ones that are closest, in other words, that have the minimum distance from this particular unknown record. And then we need to use the class labels of the neighbors in order to predict the class label for this unknown record. In this case, it is going to be a plus label, right? So we are having only two labels, plus labels and minus labels. In this case, the k value is 3. We are looking at the 3 nearest neighbors, and all the 3 have the same label. So this point is going to have the same label as date of these neighbors. If the neighbors happens to have different labels, then we are going in the typical approach, we are going to use the majority, right? So if 2 of them are plus and 1 of them is minus, so we are going to predict plus for this unknown record. If 2 of them happens to be of the label minus, then we are going to predict a minus label for this. Similarly, if we include more neighbors, for example, if we consider k equals to 5, which means 5 nearest neighbors, so then probably these two data points will also make up its neighbors. In that case, going by the majority vote, its predicted label is still going to be a plus. If we include 2 more neighbors, that is k equals to 7, right? So then probably these 2 points will also make up its neighbors. In that case, it is still going to be a plus label, since the majority happens to have a plus label. So that's how it's going to work for the simple k nearest neighbor algorithm. Okay, so a couple of points should be noted here is that this representation, that is 2D representation of these different data points or data records, or instances corresponds to when we have only two features, one feature on the x-axis and the other feature or attribute on the y-axis. So in this case, we can plot each and every data point using this two-dimensional representation. If we have three features, right, so it will be a more higher dimensional space, that is three-dimensional space, and then we will have x value, y value, and z value. If we happens to have more than three features, so then we are going to represent these points and consider them as points in more high dimensional space. In general, we can have n-dimensional space, which means n dimensions corresponding to each and every feature, and based on the value of each and every feature, each record can be considered a point in the n-dimensional space. This slide further elaborates the concept of the nearest neighbors. So in this case, we are considering one nearest neighbor. So the label of the nearest neighbor will be the corresponding label of this unknown instance, right? That will be our prediction. If we are considering two nearest neighbors, so then we are going to consider the two nearest neighbors corresponding to this particular unknown data point. And in this case, a draw may happen, so we need to have some mechanism in order to determine what is the corresponding label in this case. So here we have a draw, so then we need to have some mechanism in order to resolve these tie-breaking criteria when we are using the even number of neighbors. So this represents the three nearest neighbor concept, right? So these are easy to understand slides. The final thing is that we can employ different kind of distance matrices in order to determine the distance between one record and another record, or one data point and another data point. Some examples are Euclidean distance, Manhattan distance, city block, and many others. So you can search out the relevant literature for the different types of distance matrices and correspondingly their properties. The easiest one is the Euclidean distance, which is the generally used approach. And in this, in order to determine the distance between a particular record, such as record number 1 and record number 2, the Euclidean distance is going to subtract the value of each and every attribute. So for this object, it will take the value of this attribute and subtract it from this attribute, and then take a square of that. Similarly, for this attribute, it will subtract the value from here, this value from this value, and then take a square, and this value from this value, and then take a square, and then it will add up all these values, and that will give you the distance from this point or this data record and this data record, right? So that will be the corresponding distance between these 2 points. Similarly, for other distance matrices, it's quite easy and straightforward to calculate them. I would strongly encourage you to go through a little bit of the literature and find out the corresponding calculations yourself. Finally, this diagram represents the Bernoulli diagram, which represents the classification boundary in case of the nearest neighbor algorithm. And in this case, we note that it is quite haphazard kind of a boundary. And this means that the boundary outside this particular data point means that any point which lies within this boundary, it will be classified as the label corresponding to this particular point. So that's how the decision boundary of nearest neighbor look like. Right? So it is like small kind of areas corresponding to each data point. So each data point which falls within this area, it's going to have the label as this particular data point has. So that was a little bit intuition regarding nearest neighbor algorithm. Hope you're enjoying the course. See you in the next segment.